Um, the next is offensive stroke highly emotional questions should be avoided as much as possible. This one doesn't require much explanation because we know that you are conducting a research. There are questions that will be offensive to respondents. You don't ask them offensive questions. Otherwise, the person will say nonsense. You fold the questionnaire and throw into a trash bin. So because of that, even when you want to ask a question that may be somehow offensive, for instance, to some persons, you find a way you construct it so that nobody will be offended in whatever question you're asking. The same is with emotional questions. You don't begin to ask people emotional questions just blunt. And once it is possible that maybe you are giving, for instance, you want to conduct research on maybe widowhood, for instance, and the people that are your respondents are widows. And in giving questions, you begin to give questions that will remind them of what led to the death of the husband. Do you understand? It's not everyone that will be able to read such questions, supply answers without breaking down in emotion. So because of that, when someone is asking that a question, such a question, and you have reminded the person of all the ordeals the person has gone through, that person will start crying, may break down. And in the process of that, someone that has broken down in emotions, you will not expect that person to go back and continue to answer the questions. The person will just push it by the side, and the person may not want to go back to it again. So you try to avoid emotional questions. Even when you must ask such a question, maybe because your research requires to get such information, you still give a coloration to that, so that maybe ordinarily so the person will not maybe get breakdown. The next is questionnaire should guide the respondents into questions with possible open-ended answers. Yes. When you are giving questions, that is just like what I said before. You want to give response, you are asking someone a question. The person may not know how to answer the question, especially if it is an open-ended question. There are such questions that are open-ended. What I mean that answers for questions that are open-ended, what it means is that there are more than 1001 answers they can give. In such a situation, to help your research, you may do what? You may give a guide. You may put the questionnaire in such a way that the respondents will be able to do what? Will be able to know the responses to give that you are looking for. Not if you leave it open, maybe this group of people may begin to think of one kind of responses to give. Other people will think of another kind of responses to give. At the end of the day, you have got so much varied responses that will not be able to help you in your research. And you'll be wondering, how do I handle this thing? How do I analyze it? But you can lead your respondents to the kind of responses that you need, so that they will be able to give 1, 2, 3. You can put it in option form. That is the best way. If you have put it in option form, what it means, either 1, 2, 3, others, for instance, others specify, for instance, you find out that majority of your respondents will be able to pick either of those options that you have presented than when you leave it to be so open. That is about the qualities of a good questionnaire. And if we keep to all these qualities while we are designing our questionnaire, we can be sure that our questionnaire will be as good as it should be, and in such a way that at the end of our field work, we will be sure that we have all the relevant information that we need for our research. I hope there's no question on that. All right. So we'll go to the next slide, which is observation method. Observation method is used in experiment-based research. Every research that is based on experiment, the way to collect information is by observation method. You go to the lab to perform an experiment. There is a point when the results of the experiment is needed for you to collect. Is it not so? It could be as a result of maybe a color change. For instance, it could be, there must be something, an indicator that will tell you that I have got a point I should do what? I should collect my result. So once you get to that point, you collect your result and keep. At the end of the day, you have the data that you are going to analyze. Observation method is purely for experiment-based research. And the last one, which I did not capture in any of the slides, is the first one in the list, which is the interview method. And the interview method of data collection or primary data collection is no other thing than when the researcher or the investigator himself will have to sit with the respondents and ask questions that pertain to the research that he or she is conducting, in such a way that when the responses, the answers given to such questions will be the needed information that the researcher is interested in, which he puts down, and that forms his or her data. There are ethics that must be followed in interview method of data collection. And that's number one ethic, which is the primary, is that you don't collect data from someone you have not first of all told that you want to collect data from. I don't know if it's understood. And maybe you are discussing with someone. Indirectly, you are looking for information. You have not told the person that I'm actually looking for information on this. And you go ahead and engage the person. You just ordinarily engage the person in a long discussion. And that person may be false prey. And as you are discussing, you are asking some questions, and the person is giving honest answers to them, unknown to him or her, that probably you have a recorder that you are using. At the end of the day, you go back and play the tape, and then you get all the information you are looking for. If the person gets slow, that person, it may equally involve litigation. You want to get information from me and you never told me. If you want to get information from someone, the first thing that you do is that you introduce yourself and tell the person that I'm actually conducting a research, and the topic of my research is this, and it's all about this, it's all about that, and I have this, I am on a field work, and I'm looking for so and so information. Please, I would want you to be part of my research work, to be recruited as one of my respondents. If the person says no problem, the person has accepted. Once the person declines, you leave the person and move to another person. But if the person still accepts, again, in this age of devices, because you have told the person and the person has accepted, it's not a reason for you to begin to record the person's voice. I don't know if it's understood. That person has accepted that, okay, there's no problem, we can go on. But if you want to record, ask the person still, please, can I record your voice, the discussion? If the person says no problem, you go ahead and record. But if the person says don't record, then you stop. But in such a situation, there is what is called a schedule that every interviewer uses. What is a schedule? A schedule is a kind of a list of questions of importance to the researcher. He has placed it in schedule. There may be only 5 questions that are of importance, which responses to those 5 questions are of importance to the research. But of course, in interview, you might even begin to discuss things that are not relevant. Maybe in the country now, almost every person that you meet will begin to tell you how things are biting, and then you may open that up, and people will begin to discuss the biting economy. In the course of the discussion of the biting economy, you now begin to drop your questions as they occur. But what equally happens is that if one is a good interviewer, you don't get overwhelmed by the discussions. How do I mean? You don't get maybe consumed in the discussion that you won't be able to get your information again. No matter how, there are people that are wonderful discussants, that you bring a topic, for instance, on the economy of the country. Wow, you have opened, it's like they've taken light too. Okay. So there are people that are wonderful analysts, economic analysts, that if you go to them and you open up the issue of the economy of the country, they will start. They will begin to give you all the economic terms, all the economic policies, starting from the time Chukwuma Soludo was the governor of CBN. He brought up this policy, he called it this, and after some time, he tested, they did a pilot survey on this policy, maybe in 2 local governments in Jigawa State, and how it was working, and they now extended it to maybe 60 states until when they now saw that it has failed. As he is finishing that one, he brought up that when this other governor of CBN came, he changed this policy and introduced the other policy. You yourself, every human being likes to be educated, isn't it so? Especially if you are not knowledgeable in that aspect, you will just do what? You will be listening. And the person will take you through. For more than 1 hour, he is analyzing the economy of this country. And at the end of the day, you have learned a whole lot of new things. But the purpose for which you engage the person, 100% defeated because you didn't get anything out of it. Instead of getting, you are just gaining economic knowledge. I don't know if it's understood. So, because the interviewer, in every discussion, the interviewer holds the what? The ace. That he decides the direction of the what? Of the discussion. Even when the person is moving and is giving you the history about the economy of the country, find a way without offending the person, without maybe shunning the person, find a way to do what? To redirect the person to the what you are looking for. I hope it's understood. By redirect, at every moment of the time, it is your duty to be what? To be bringing the person back to what you are discussing until you are able to get all the information you are looking for. So if the person has declined that you should not record his voice, you use the schedule to do what? To be putting down the responses that pertains to the what? To the research you are doing. But if the person has accepted that you should record, you go ahead and record. You don't need any other thing. At the end of the day, you just go home and play the tape and extract all the information you are looking for. I hope that is clear. That is for interview. And there are 2 different types of interview. One is face-to-face interview. The other one is telephone interview. Interview can be granted on telephone. You can reach out to your various respondents on telephone and get whatever information you are looking for from them. At the same time, it can be what? Face-to-face. Whichever one. What is important is that you get the information that you are looking for your research. I'm sure that is clear. So we will leave that at this moment to go to data analysis and interpretation. So all that we have been discussing as we ended yesterday and continue today, we have been talking about data collection, how to collect data. Is it not so? Whenever data have been collected, that is not the end of the research. Okay, have a question. All right, go ahead.
In this interview method, if the respondent declines your recording or information and you need it for your research, what do you do?
No. If the respondent declines what?
Declines that you record whatever information that you need.
Yes. But I have said it before that there are maybe, let's assume there are 5 information that you need for your research. It is your responsibility to put down those questions on a piece of paper, and that is what I have called a schedule. You put it down. In the course of you ask a question, for instance, and the person is just a discussion. In the midst of all the many things the person will say, maybe there is one that answers question 1. You put it down. Do you understand? Without telling the person that the person doesn't know what you are putting down, but you are noting something down. At the end of the day, what you have noted down becomes your data. Is that clear? Yes.
I want to ask about observation.
Okay.
I've attended a program where the person that anchored it was talking about participants and non-participants observed. So, is getting this consent, is it restricted to a particular group of people? Or is there a particular type of research that you don't need to gain this consent?
For them to be part of your work.
Yes, assuming you want to understand or to study the behavior of some certain group of people, maybe antisocial behavior.
Okay.
For example, you know that obtaining their consent they may not really like to give consent. And if there are conditions that you don't need this consent, maybe you stay in the environment and you are trying to understand how certain group of people behave. I don't know.
The question that you have asked is good. Talking about the issue of getting consent from respondents. There are situations where such is possible or that is not possible for you to get information from them, where it is not possible for one to get information, okay, when you have asked for consent. There are such studies. I don't know if it's clear. But in such a situation, depending on the sensitivity of the research or the nature of the research you are conducting, in such a situation, you need to put it down. Do you understand? There should be somewhere in the work where it is stated that you did not get the consent of these people. Do you understand? And the reason for that is that if it is possible, such a work, while publishing it, for instance, no locality will be mentioned. Anything at all that we trace to those respondents should not come in. Do you understand? There are actually some research work that people do that they use what they call maybe pseudo-identity. I don't know how do I mean? There are some agencies in Nigeria, for instance, even in this country today, that if you want to study their company, or their establishment, you cannot publish it. So in such situations, when you finish such a research, there are two things possible for you. Either that you don't put it anywhere to trace the respondents, or you give a pseudonym. I don't know if it's clear. But if you are going to conduct the research when you have not gained the consent from the respondents, and at the end of the day, while reporting your research, you put it in such a way that those respondents can be traced. In such a situation, if they take you to court, they will begin to claim damages, and it is not ideal in a research. I hope it's understood. If for any reason you are conducting a research that doesn't, you know very well that if you are seeking for consent, that you won't be able to get consent, and you need to do the research. In such a situation, there's no problem. But every single thing that will bring about a trace of the respondents should not appear in the publication, shouldn't appear in the work. I hope it's clear. So you don't maybe tell someone that you are carrying out a research about these certain people, like you have mentioned, antisocial behavior, and it is in so place and so place. When you publish it, even the respondents themselves may be part of the people that are going to read your publication, and they will begin to see, oh, so this is happening in this place, and I belong to this group. Do you understand? So we are behaving like this and we are behaving like that. Who conducted this research? If the person has any trace of the fact that you actually ask him or her any question, the person will take you to court. I don't know if it's clear. All right. So we now go back to what we are discussing, data analysis and interpretation. I was saying that all that we have discussed is how to generate data. But once data have been generated, how the data is analyzed is equally important for our research, because there are stages that we pass through. Number one stage is to conceptualize a work, and then to do all the background works, then go to the field for data collection. When we have gone to the field to collect data, the way the data is analyzed is very important for the research. If you analyze it in a way that is wrong, then no matter how beautiful the data you have collected may be, because of the fact that the analysis is wrong, everything about the research becomes wrong. So it is important that we analyze data correctly. So when data have been collected and presented, there is little or no information that can be elicited from such data, unless they are subjected to statistical means of eliciting or validating or otherwise information. So when we have it, we are just presenting, carrying the data. There is nothing that data can say. Data doesn't speak. Do you understand? Data doesn't speak. Data doesn't give you any information. All one knows is that I have data. For one to be able to have information from data, it must be subjected to analysis. So these statistical means of getting information from any set of data is what we know as what? Data analysis. And there are different analytical tools that are used in statistics. We will mention them. Number one is the descriptives, which we call descriptive statistics. All of us will know descriptive statistics. Is it not true? Do we know descriptive statistics? We know it. From our secondary school, we are doing descriptive statistics. We did mean, median, mode in secondary school. That is descriptive statistics. Any type of statistics that begins and ends with what? Computation of just getting summary values is descriptive statistics. How do I mean? When you obtain the mean, maybe you are carrying out a research, or part of your research is to know the average duration of a particular ailment. In other words, once somebody is infected with a disease, how long the lifespan of the disease. How long is it expected to stay before the disease is cured? For instance, if that is maybe a part of the research that one is doing. At the end of the day, you are asking the patient maybe how many days or how many months or how many years, depending on the nature of it. You will have various values obtained from different patients. So when you have obtained all of this, you are now looking at what? The mean length of time. Do you understand? So whatever is the mean length of time, you report it. It is what? A descriptive statistics, because it is summarizing the whole data, so that you will be able to use one value to do what? Represent a set of data. So whenever we are carrying out whenever we are doing such computations, we are discussing descriptive statistics. I hope it's clear. So, but for descriptive statistics, even when a descriptive statistics, when it is going to be used, to make reference to a population, is no more just descriptive statistics. Does that make sense to us? I said, even like that mean that we know, which we have called a descriptive statistics, when the essence of the reason for obtaining the mean is for one to be able to do what? For one to be able to talk about a population, then it's no more what? Descriptive. It has become an inferential statistics. Descriptive statistics begins and ends with the what? The data. If, for instance, somebody is looking at the mean age of students and collects a sample and then uses that, and at the end of the day obtains the mean age, if it is descriptive statistics, then the result will end with what? That the mean age of these 20 students is equal to maybe 22.5. I hope it's clear. It ends at that point. But if there is need for you to use that 22.5 to make a generalization for a larger group of students, it is no more what? Descriptive statistics. So every descriptive statistics begins and ends with data that is what? Before one. I hope it's clear. Now the next type of statistics or statistical tool is the tests of hypothesis involving proportions and interpretations. Another is the test of hypothesis involving means and their interpretations. Another is measures of association. Then another will be graphs and plots. And when we take the descriptives, I have discussed extensively about descriptive statistics. When we are building frequency tables, when we are computing percentages, when we are computing the means, computing medians, computing modes, computing variances, computing covariances, we are discussing descriptive statistics. They also include visuals that can be used to show frequency tables. There are so many visuals that can be used to show frequency tables. So whenever we are computing all of these, we are discussing descriptive statistics. But if computing these things will be used to make reference to a larger population, it is no more descriptive. It now comes to an aspect of statistics that we call estimation. We are now estimating whatever thing that exists in a population on the basis of what? A sample. Basically, statistical inference. There are only two aspects of statistical inference. And what are those aspects? Only two of them. Number one is estimation. Number two is what? Test of hypothesis. These are the only two things that make up what you know as statistical inference. It's either you are estimating something that exists in a population on the basis of a sample, Like the example I had given before, we are talking of the mean age of a student. Under descriptive statistics, you get the mean age of maybe a sample of 20 students to be 22.5 years. That ends there. But if we are using those sample of 20 students to study a population of maybe 100 students, and you are now going to take that, generalize the mean age of those 100 students on the basis of this 22.5 which you have obtained from the sample, it has left descriptive statistics to where? Inferential statistics, where you will now be talking about estimation. In such a situation, you will now be saying that the mean age of a population of 100 students somewhere, which is your target population, is estimated as what? 22.5. I hope it's clear. Most of the figures that we hear in the country, for instance, all of them are based on what? Statistical estimation. Sometimes you will hear, according to statistics, that the incidence rate of HIV in the country is this. I hope it's clear. And the question will be, how did one get to that? It's very simple. It is simply by estimation. Maybe you come to a locality or you get a group of persons and then you begin to do what? Out of a sample of like 100 persons that you have got, how many of them have HIV? Maybe it is only one. So it is 1%. You can now generalize it for that particular, the whole place. It may be a state that the incidence rate is what? Just 1%. I don't know if it's clear. So it is just purely by what? Estimation. And that is what we know when we say according to statistics, we have talk about this figure, we talk about that figure. All of them are based on what? Estimation. So, in terms of tests involving proportions, we know what a proportion is. A proportion is not that thing than maybe there is a particular variable of interest to you and you are looking at maybe the rate of that particular variable in your study population. You have a data set out of the data and this is what you have identified. You will now be asking how many out of that your sample, random sample has that particular attribute or has that trait. If maybe the proportion will be what? X all over what? Number of the sample that you have. So when you have that, the next question is, we subject it to different what? Tests. Because it is not just when you have obtained a particular proportion, you will say that, yes, I have obtained it and it is estimating. It's good, but you need to do what? Conduct a test of hypothesis about that proportion to know if it is true. There are some studies that you will be doing and you will have a standard rate. Is it true? There are some studies that maybe in the literature it is known. Let me give an example. According to 2000, unfortunately, Nigeria has not done census for a very long time. The last census in the country was done in 2006. Some time ago, it was rumored that we are going to do census. I don't know what happened. And even when they had trained some people to be ad hoc staff for the exercise, something happened. Maybe snake ate the money that was meant to be used for it. So it never came. So according to statistics, 2006 census, I can't remember the figure actually, but it was estimated according to that we have more number of maybe the males in the country were like maybe 52%, while the females were 48%. That was that. Okay? Yeah. What was obtained from that census. So when we now begin to have it that whenever I have a population obtained from the country, I will expect to have what? 52% of that population should be what? Males. While 48% should be what? Females. If I want to use it to build a proportion, I will be able to have proportion of females in the country, which will be what? 48 over what? 100. 48% or 0.48. I hope it's clear. So that is what is known. Now, if I want to embark on a study, and it has to do with maybe proportion of females in my study population, that is what I know. It's a standard because it has been published and they can be quoted. I may, in my study at the end of the day, I may have a proportion, which is proportion of females I have obtained from my sample. I will now be checking, does it conform to that standard? Do you understand? Does this, I know that there is a standard proportion for females and this standard proportion is 0.48. So what I have for this particular study, what I have obtained, does it conform to that standard? So for me to do that, I will be carrying out a test of hypothesis to determine if what I have obtained is the same with what is the standard, or have I obtained something that has deviated significantly from the standard? I hope it's clear. So if I am engaged in such a study, I will need to test it, and it becomes a test of hypothesis involving a single proportion. I hope it's clear. It's a test of hypothesis involving a single proportion. Again, there may be two different proportions that I'm interested, and my question will be, are they the same or do they differ significantly? Do I have the same proportions for these two, or these two proportions, do they differ significantly? When it comes to that, I will be conducting a test of hypothesis involving two proportions. In other words, trying to test for the difference of two proportions. The last one there is test of hypothesis involving several proportions. And the test of hypothesis involving several proportions is what we may call analysis of what? Frequencies. Because actually, I'm sure that we understand that proportion is the same thing as the frequency, if you look at it the other way, because when we talk of frequency, we use frequency to obtain what? Proportion. Is it not so? If, for instance, in a group of 50 persons, then we are looking at the frequency of males in that, let us assume that the frequency is maybe 10. We can use that to obtain the proportion. Proportion becomes what? 10 all over what? 50, which is the total number. I hope it's clear. So when we are talking of testing for frequency, the same thing as testing for proportion, or vice versa. So this analysis of frequencies, and there are two types of them. One is a one-way analysis of frequency. The other is a two-way analysis of frequency. In one-way analysis of frequency, it is called what? Chi-square goodness of test. Actually, in the test of hypothesis involving several proportions, it is the only statistical tool that is used for it is what? Chi-square test. I hope it's clear. What chi-square is in statistics, let me start this way. We have several statistical distributions. Some of us that have done a little of statistics will understand that we have different what we call statistical distributions. The most popular one is the normal distribution. Has anybody heard of normal distribution here? I am sure at least one person must have heard of it. Even if the whole of the rest have not heard of it, one person at least. So we have what we call statistical distributions. So the statistical tests are based on those distributions. We have what we call discrete distributions and continuous distributions. Discrete distributions will have things like binomial distribution, Bernoulli distribution, Poisson distribution, and the rest. But in continuous distributions, we have things like normal distribution, chi-square distribution, exponential distribution, and the rest. Maybe, sorry, it's like I'm saying what I'm not supposed to say. But I'm only trying to make an explanation. And I'm thinking that I have veered off. Let me retrace my steps. So, but what I'm trying to say is that one of the statistical distributions is known as a chi-square distribution. So, statistical tests are actually based on statistical distributions. We will still come to that. When we are testing for single proportion, it is a normal test because the proportion of anything that one is looking for in statistics is said to follow a normal distribution. Therefore, tests for single proportion or tests for difference of two proportions, both of them are what? Normal tests, depending on the size of the sample. If the size of the sample is small, a normal distribution in statistics again approximates to another distribution, which is known as what? T distribution, when the sample size is small. A T distribution, equally, if it becomes large, becomes equal to normal distribution. Therefore, if the sample size is small, single proportion test becomes a T test, because what we will use to arrive at our result follows what? A T distribution. Difference of two proportions, if the sample sizes of those two different attributes that we are checking if their proportions are the same, if the sample sizes are small, difference of two proportions will follow a T distribution. Therefore, it becomes a T test. Majority of you have heard of T test, is it not so? T test is actually a type of test, a statistical test, where what we call test statistic follows a T distribution. So, the point I have made here is that single proportion test and the test of two proportions test can be what? A normal test or a T test. Normal test if the sample size is large. T test if the sample size is small. And the next question one may ask now is, when do we say that a sample size is small? And when do we say it is large? For us in statistics, there is no cut-off point that is generally accepted. But for us in statistics, any sample size that is more than 30 is regarded as a large sample. For us in statistics, anytime you have a sample size that is more than 30, we regard it as what? A large sample. But if the sample size is less than 30, we say it is what? A small sample. So when we are carrying out tests of hypothesis involving proportions, if the sample size that we have used to obtain those proportions are less than what? 30, then the test of hypothesis will follow what? A T distribution. So it becomes a T test. But if the sample size is more than 30, or in fact from 30 and above, we will say it follows what? A normal distribution. Therefore, the test becomes what? A normal test. Another way of presenting normal test is what we call Z test. Okay? The reason is because every normal distribution can be standardized. And there is what we call standardized normal distribution. It becomes what? Z. We call it generally Z. A Z distribution is a standardized normal distribution. And for us to be able to carry out any test, which is a normal test, we must standardize it so that it becomes what? A Z test. So we have Z test and what? T test. T test when the sample size is small. Z test when the sample size is what? Large. I hope it's clear. But for For several proportions, we no longer have a t-test, we no longer have what? A z-test. Rather, what do we have? A chi-square test. It is a chi-square test that we use to test if several proportions are equal. And there are two ways. We say the one way chi-square test, we call it chi-square goodness of fit test. A simple example I may give is this. Let us assume that I know before, when we are growing up, we were made to understand that there are 4 blood groups. That's what we knew when we were growing up. But later on, I began to hear there are many other blood groups, okay? But let us say, I know that is your area. So you can educate me very well on that. But for now, let's leave the education and I still assume that there are 4 of them. Is that clear? A, B, and what? O. Let's assume that. Let us equally assume that there is in every population of human beings that there is a standard ratio of these 4 blood groups. Do you understand? Let us assume that maybe blood group A takes that maybe 10% of human population has blood group A. That 20% has blood group what? B. All these are assumptions. Let's assume that together they are what? 30%. You know, so we are left with 70. Let's assume now that 15% have blood group what? AB. For instance, how many do we have left? 55. So let's assume that 55% of the population of human beings have blood group what? O. If that is what is known as a standard in the literature, now I have carried out maybe a research on blood group, and I want to see if what I have, that population, conforms to that standard ratio of blood groups. Do you understand? What I will now need to do is that there is a proportion of blood group O, there's proportion of blood group AB, there's proportion of blood group what? B, and there's proportion of blood group what? A. Each of them have proportion. These percentages we are talking about simply means that 10 out of every 100 has blood group A. 20 out of every 100 has blood group what? B, and so on. What it then means, these are the proportions that are known in the literature. I will now, from my own research, I want to test. I have a sample of individuals. I have measured their blood groups. But when I have finished it, I want to check if my study population conforms to that standard that is known. In this case, we can now see that there are how many proportions? There are 4 proportions. So we are now interested in checking what? The difference of 4 proportions. And the standard doesn't say that they are equal, but it has given what? A pattern. I hope it's clear. So we will now be testing whether it conforms to that standard. And this is what we call chi-square goodness of fit test. We want to fit our data to the standard proportion. Do you understand? To see if it fits to that standard. It will fit to that standard no matter the study population that we are studying. If we have proportions of these blood groups that are patterned after that standard pattern, we will say that we have what? We have fits perfectly to the what? To the standard. Fit test. The data we have obtained, we want to pattern it to a standard. But there is another type of chi-square test, which is now two-way test. It is called the chi-square test of independence. What do we do with this? If we are to look at it, we'll find out that there are now two different ways. While we have maybe a kind of values of the pattern of this broad group in one direction, we have yet another factor, another variable in another direction. So that when we are building them, we are now trying to check, does it depend on this? How do I mean? I want to use that example of broad group pattern to complete this example. Let us assume that we have maybe 3 segments of that population. It's possible that that population will have 3 segments of it. Do you understand? I will now be looking at, does this pattern, does it depend on segments? In other words, is it possible that as you move from one segment to the other, that the conformity to this standard will be changing? I hope it's understood. We have broad groups A, B, AB, and O. Then we have segments of the population, segment A, segment B, and segment C. We will be checking if the distribution of these persons, distribution of this population, their broad group distribution, does it depend on the segments? Do you understand? It will be so. It will depend on the segment. If the pattern of the distribution of the broad groups for segment A is significantly different from the pattern of the distribution of broad groups for segment D, and maybe significantly different from the pattern of distribution of the broad groups for segment C. But if all of them are the same, irrespective of the segment, the distribution in segment A does not differ significantly from the distribution in segment B, which doesn't differ significantly from the distribution in segment C. What it simply means is that the distribution does not depend on the segment. Whether you use segment 1 or you use segment 2 or you use segment 3, the distribution remains what? The same. I hope it's clear. So when we are carrying out this test, we are calling it what? Chi-square test of what? Independence. We are testing for independence of the segments as it concerns what? The distribution of the broad group. That's just a particular example. I'm sure it is understood. So when we are discussing that, we call it a chi-square test of independence. So just as I have said, we have chi-square test that is called goodness of fit test. We have one that is called test of what? Independence. Unfortunately, we will not be able to begin to maybe do a practical data analysis here, because if we are to do it, then 1 week will not be enough for this workshop. I don't know if it's clear. 1 week will not be enough, because each of them that we meet, we may spend hours discussing that one after we move to another. But what is important is just to give us a guide. The reason is because, especially in this age, nobody stresses himself to begin to do all these analysis by these manual computations. For us, we don't. What we do is we use softwares to do these analysis, which I'm sure that people are aware of, that softwares do the analysis. But it is important, as we are looking at all this, that we begin to have an idea of what softwares do for us. There are so many statistical softwares that can be used to carry out all these analysis. And of course, I don't think we are not going to be discussing softwares here, but there are such statistical softwares. The one that appears to be the most popular is what they call SPSS. Is it not so? I'm sure that all of you know that one, SPSS. Even though SPSS is called what? Statistical package for what? Social sciences. And when it comes to that, we always, for us, we always say that we are not social scientists. For me, I'm not in social science, so I don't use SPSS. I used to use SPSS so many years ago, but after some time, I stopped using it. I stopped because it's not meant for me. It has a lot of limitations. There are so many things it cannot do. And because there are so many things they cannot do, we resort to more robust statistical packages that can satisfy us that are in statistics. And we have a good number of them. If we are using something like, there is a statistical package, which of course is the most robust statistical package that we use, that is called R. I don't know if anybody has heard of it. The name is just R. Yes. Yes, like Richard, R. That is the name, R statistical package. That's what we use. It has another mimic package. There's another package that mimics R, and that package is called Python. So it's either we use R or we use Python. So they are the packages that we use. We don't use SPSS, but it can be used though. I'm not saying any result that you get from SPSS, I'm not saying that it's going to give you a wrong result. Do you understand? It gives an accurate result. I can trust SPSS, even though presently it's no more called SPSS. I'm sure we still know. SPSS was bought by IBM, I think 2 years ago or thereabouts. So it's now called SPSS IBM. It's bought by IBM company. So it's no more. If you write it anywhere, report that you have used SPSS, somebody will be looking at you that you don't know what you are talking about, because it's no more called SPSS. It has been bought by a different company, and the company is IBM. So it is SPSS slash IBM. That is the name. Okay, hyphen, sorry. But you should have said it out. So SPSS hyphen IBM, that is the name. Okay. If once you have it, you are good to go. You can always do your analysis. I usually recommend that even students, you can learn how to use all those packages. The reason is because maybe today you're a student and you are just carrying out a research so that you will be able to finish your program. But after the program, you may begin to do independent research. And it's not every time you have research to do that you are looking for someone that will be analyzing for you. So if you learn to do it by yourself, that is the best. So at any point in time that you are conducting research, once you come to data analysis, you just put in your data and then click the button and then get the results and use the result to do whatever you want to do. And these are what I call generic statistical packages. There are still some specialized packages that are used for specialized purposes. I don't know if you understood. I don't know, I don't work in health sciences, so I wouldn't know the specialized packages that can be used in health science, but I know there are different areas have some specialized packages tailored for doing whatever thing that they do. But when you begin to hear of those names, they are specialized for a particular thing. They cannot do other things. But the ones I have mentioned are generic statistical packages that can be used to do so many things in statistics. Okay, that's about chi-square test or test of proportions. When we go to tests involving means, it is just like the test involving proportions. There are tests involving single mean. Yes. There's no problem. Go ahead. Okay. I should revisit chi-square test of independence. Hey, okay. Let me try. Can you tell me Just tell me one research you are doing that involves chi-square test of independence.
I don't think you have a research I'm doing about it.
Okay, just tell me something, a research that can be done in your area that involves chi-square test of independence. Just anyone that can be done. Because you have been hearing of chi-square test of independence. So you should be able to have just an idea. Okay, just say it. Use of library by student nurses. So tell me a little more about that research. Can you explain a little more about it? Use of library. Personally, I don't understand what you meant by use of library. Do you understand? So if you can explain it to me.
Okay. Use of library by student nurses within this
Okay. Okay. For them to be able to make use of the library books or library materials, right? Okay. The use of library by the student nurses. Okay. The undergraduate nursing students, right? Okay. Yes. We can make out chi-square out of it. Let us assume that these undergraduate students, nursing students you talked about, okay, let us assume that we have measurements of their use of library. Let's categorize the measurements for their use of library. Let's have number 1, frequent users. Okay? Let's have number 2, rare users. And let's have number 3, no users. Do you understand? There are 3 of them. Is that clear? So, when we go to the Department of Nursing Sciences and then take a sample of, say, 50 students, our question will be the extent to which they do what? They use the library. Some will say, I frequently use the library. Some will say, I rarely use the library. Some will say, I don't use the library. We may decide, because these are just by text, the information they are giving to us. That falls into the type of data that we were talking about yesterday. This is what? A nominal data. Do you understand? Which means we can decide to code them 1, 2, 3. 1 is what? Never use. 2 is what? Rarely use. And 3 is what? Frequently used. Good. These students again, we know that they belong to different classes, different years of study. Okay? Is it not true? We have first years. Unfortunately, first years are they here? So the people that are here from second year to final year, is it not so? Good. These students, we can as well get their years of study. The first variable of our interest will be is what? Their year of study. The second variable is what? The rate at which they use the library. Is it not so? These 2 information is what we have obtained from them. Our interest will now be that there is going to be a pattern of use of library. The pattern will be what? Those that are frequently using, those that are rarely using, and those that are not using the library at all. We want to see if this pattern of the use of library by these students, if it depends on what? On their year of study. It is possible that when we put all of them together, there are 50 students. Maybe 20 of them will say that we don't use the library at all. Okay? Maybe 25 will say what? We rarely use the library. And what is left now? We are left with 5. 5 we say we frequently use the library. That is the general pattern of these nursing students. These 50 nursing students we have selected for our study. I hope it's clear. But we don't know. When we go year by year, year of study by year of study, will they still maintain this general pattern? Or will they begin to differ as we move from one year to the other? Do you understand? So because of that, we will be careful to do what? To obtain samples in such a way that every year will be what? Adequately represented in our study. So we have maybe on the columns like this, where we have the responses on the use of library, which will be don't use, rarely use, and frequently use. There are 3 of them. We will have their, on the row side, we will have their years of study, which will be what? 2nd year, 3rd year, 4th year, and 5th year. Do you understand? So we begin to put them. We begin to put the values for each of those for each year. Do you understand? In other words, we are distributing this sample so that it will cut across. For those in 2nd year, those that don't use from 2nd year, we put it under don't use. Those that rarely use in 2nd year, we put their number under rarely use. Those that frequently use in 2nd year, we put their number under frequently use. We do the same for 3rd year, 4th year, and final year. And then the total will be the what? The total frequency of how they use the library. I hope it's clear. Our problem will now be this total frequency of how they use the library. Does it conform? Is it the same across the years? It is possible that for 2nd year people, majority will be using the library, while the very few don't use the library. But it is possible that in 3rd year, majority don't use the library, but very few rarely use, and even no person frequently uses. Do you understand? When you begin to see it in that way, there's what? There are differences in their pattern of use according to their years of study. So this is a chi-square test of independence. We want to know if the frequency, if we want to know if the distribution of the use of library by these undergraduate nursing students, if it depends on their year of study. And it will depend on their year of study if they have different patterns as we move from one year to the other. Why it does not depend on their year of study if there is no significant difference in their patterns as we move from one year to the other. I don't know if I have I succeeded in clarifying that? Okay. Yes. Okay.
For this instance, let's say in an option
Okay. That becomes a different type of analysis altogether. Again, if we want to analyze that, you know that it is an open-ended question. You know that first of all. So when you have, it's either you give them a guide so that it will be possible for you to, because I have told us before now that the type of anything that is called statistical analysis doesn't understand alphabets, it doesn't understand the words. When you are just speaking grammar, statistics doesn't understand the grammar. The only thing it understands is what? Figures. So, for you to be able to convert those reasons into figures that you will be able to analyze, you need to give a guide. But even when you did not give a guide, as you are asking the question, when they have given their varied reasons, it's now left for you to look at all those reasons and classify them. You are going to categorize them for you to be able to analyze it. Do you understand? You may categorize it into maybe 3 different groups, for instance. And when you now, if they are categorized into 3 different groups, that becomes a different analysis. First of all, you have established, number 1, that their usage of library is dependent on their year of study. That is the end of that particular segment of your research. Then the next segment is reason why they don't use the library. Do you understand? When it comes to that, you are going to sieve out those responses that don't use the library. Maybe your sample size is 100. It's possible that only 30 of them say that they don't use the library. So in this analysis, you are no more analyzing the 100. You are not analyzing only the 30. Do you understand? Because it's only 30 of them that are concerned with this. So when it comes to that, you have the 30, you have maybe 3 different segments of why they don't use the library. Okay? Now the question will now be, out of these 3 segments, it's possible that you may equally be measuring maybe frequencies. For instance, like 30% don't use the library because of this. 42% don't use the library because of that. Another percent doesn't use the library because of that. I hope it's clear. And again, if again you equally want to, because those people, you know already, maybe their gender. These 30 persons, you know their gender. You may begin to ask this question. Their reasons for not using the library, does it depend on their gender? Depending on the information you want to get from your research, there are so many other things that you may begin to ask, and that will inform how to do what? How to analyze that. I don't know if I've answered that. Yes.
This standard talking about, are we getting it from one study, or is it that different studies are used to do the standard?
Okay, in a particular field, there is no, it is difficult to get a standard from a single figure, a single study. Single study doesn't make a standard in a field. If there is a standard, it is that maybe someone has set this as a standard, and the subsequent researchers have tried to do what? Criticize it. And in their criticisms, they have always still done what? They have always still seen it to be what? To be correct. So when we are talking of a standard in the literature, one study cannot make a standard in a literature. It has to go through several studies, and if it is maybe tried by so many authors and it still remains what? The same, it is only then that one can say that this becomes what? A standard. If somebody has carried out a research and come up with something and presents it in the literature, that is like what I said yesterday, that when something is in the literature, it is subject to what? To criticism. It is when it has been criticized by so many other authors working in the same area, and it still stands the test of time, that it becomes what? Generally acceptable. I hope it's clear. A standard is a generally acceptable statement. A standard is not just something that one person has maybe come up with. Is that clear to you? All right. I don't know when I got to this point. Tests involving means. There are tests involving single mean, 2 means, the same way we did in proportions. I will not explain them again. And then several means. But when it is a single mean, it is a t-test or a z-test. The same thing we said for proportion. When it is difference of 2 means, it is t-test or z-test. Exactly the same way, depending on the what? The sample size. But when it is test involving several means, it becomes what we call analysis of what? Variance, which is called ANOVA in short. ANOVA is a test involving several means. You are testing the difference between or difference among several means. Of course, severality of means can begin with 2. Do you understand what I mean? Severality of means can begin with 2. So in other words, when you are interested in comparing 2 different means, then you can still use what? ANOVA. Even though z-test or t-test will still give you the same results. I hope it's clear. But when, of course, it becomes up to 3, 4, 5 and above, there's no other way of analyzing it except what? The use of ANOVA. I'm sure it's clear. And let's understand that when we are carrying out a test of hypothesis involving means, it means first of all that the data we have, that we can compute means on them. Yesterday I told us that it's not every type of data that can allow computation of means. Do you understand? When we have like ordinal data, when we have nominal data, you don't compute means on them. The only place where you can begin to compute means is in what? In the interval data and the ratio data. I hope it's clear. What it means is that if I have maybe this kind of maybe ordinal data, for instance, you are going to a field, it is a survey where you have talked about maybe 4 different responses, 4 different ordinal responses. Like you might say you have which example will I give now? Maybe it is an opinion poll and somebody says, I don't agree as 1, agree as 2, strongly agree as 3. Which other one? I want them to be 4. Eh? Okay. Okay, let's have strongly disagree as 1. Strongly disagree as 1, disagree as 2, agree as 3, strongly agree as 4. Good. Okay, you want to be neutral. Sorry, we are not conducting a particular research here. Okay? This is just for the purpose of what? Illustration. You are free to have neutral in your own research. But for now, we have 4. So we have given it, this is ordinal data. Because strongly disagree is lower than what? Disagree. Is it not so? Disagree is lower than what? Agree. And agree is lower than strongly agree. So when we have put it in that form, it is what? Ordinal data. Then in this ordinal data, somebody may now begin to say, what will be seen as your data will be 1, 2, 3, 4. Either 1, 1, 1, 2, 3, 4, 1, 2, 3, 4. That's the whole of thing that you'll be seeing. It's you that you are the one performing the research. So you are the only one that knows that 1 means what? Strongly disagree, and so on and so forth. So when you have this, and somebody will begin to say, let us find the mean response. For instance, mean cannot go there because it doesn't have a meaning. But if you put the mean of those 1, 1, 2, and 3, 4, it will give you a result. Is it not so? But that result cannot be interpreted in real life. It doesn't have a meaning. So that's what we are saying. And because of that, you cannot compute the mean of that. And if you can't compute the mean, you can subject it to a test that involves mean. That's what we are saying. It is only when we have things that we can compute their mean that we begin to talk of what? Tests involving the means. I hope it's clear. So the other one is a test involving variances, which is rarely done in most research. It's rarely done. Maybe you want to test for variance. There are different tests that can be used for maybe to testing the variance or difference of variance or ratio of variance. We all know what variance is. Variance is simply the average deviation of a set of observations from their mean. How far apart a set of observations are from their mean, from their central point, that is measures is variance. A measure of it is what you know as variance, which can as well be called standard deviation. I hope it's clear. Because standard deviation and variance are the same measure. If you find the square root of variance, you get it to be what? Standard deviation. If you get standard deviation, square it, you get what? Variance. Two of them are measures of dispersion, variability of variation. And what they do is to measure the extent to which a set of data are far apart from the central point. I hope it's clear. There are different measures that can be used to do that. For the single variance test, one may use a test that is known as, it is a t-test. T-test, in the literature, it is called the Levine test for variances. So it is t-test. The next one is test involving difference of two tests or ratio of two tests, is called an F-test because it follows F distribution. We will not discuss it in details. I did not tell us that analysis of variance is equal to an F-test. Did I tell us that? Analysis of variance is equal to an F-test because it follows F distribution. Okay? Just like analysis of frequencies is a chi-square test. Analysis of variance is an F-test. F, there is a distribution in statistics that is known as F. It is named after the person that gave us that distribution. The name is Snedeker, F Snedeker, but he chose to use only F. The surname of the person is Snedeker, while his abbreviation is F. So he chose to use just F distribution. Just like the T distribution. T distribution was actually developed by someone, but he chose, that person was like the way you are working for your program, that person was working as a student for his program, and they came up with that distribution. And because of that, he decided to use a pseudonym. He doesn't want to use his name. He doesn't want to name himself after that distribution, so he named the distribution after the word students. So it's called the students T distribution. That is why if you see anywhere it is written in full, it is always called what? Students T distribution. So those tests that follow T distribution, they actually follow students T distribution. The name of the person that developed it is called Gosset, but he chose not to use his name. He decided he preferred, because he is a student, he said, let it be students T distribution. So it follows F distribution, and that's all about that. Yes?
Please, you say that analysis of variance is called F-test.
It's an F-test, yes.
F-test.
Yes.
And analysis of, but you say that in single variance, we use T-test.
Yes. I said so. When we say T-test, F-test, it's not any other thing than the distribution the statistic follows. Okay? Like when I say that single proportion follows either Z-test or T-test, it is talking about the distribution that it is following. So that's what I mean by that. When I say it's an F-test, it means that for me, okay, maybe I will explain that better somewhere. But let's just note it the way it is. I just remember that maybe there's a place I will explain something close to that. Okay? But variance follows T-test. Difference of variance follows F-test. Variance itself follows T-test. That's what I said before. So, these are like different ways of representing. When I talked about descriptives, I said when we just compute single values about a sample or about a data set, we call them what? Descriptive statistics. And there are different ways of representing them using visuals. I made mention of it in that place. One of the ways of representing data using visuals is the use of histogram. Like what we have on the board is a histogram, and with the histogram, what it measures is what? Here, it measures the classes. We have put a set of data in what we call frequency table. When we have put it in a frequency table, it means that all the observations have been what? Collapsed into what? Into class intervals. And when we have it, the x-axis of this graph will contain the what? The class intervals. While the y-axis will contain the frequencies of those classes. So here it says, for instance, the first class, which is the class of observations from 15 to what? 16, has a frequency of what? 2. And so on for the rest. So when we have data presented in this form, which is a descriptive statistics, we say we have it to be as in is a histogram. The next one is what we call frequency polygon. Sorry, the cumulative frequency graph, which we know is in our secondary school days, we used to call it what? The ogive. Yes. It's a very important statistical tool that can be used to present frequency table. So it is called the ogive. When we look at it again, it has similarities with the histogram, but it's not exactly as histogram. One histogram is a block chart or graph. This one is a line graph. Now, what do we measure with that? The x-axis still represent the what? The class intervals. But in histogram, the y-axis measures the frequency, but in this case, the y-axis measures not the frequencies, but what? The cumulative frequency. Okay? Y-axis here measures cumulative frequencies, while in the histogram, y-axis measures only the frequencies. The next way we can present it is using what we call frequency polygon. Frequency polygon is something that converts the histogram to a line graph. You can, if you look at it and compare it with the histogram, we will see that they are almost the same. When we see in this frequency, in this histogram, if we maybe we measure the centers of each of these peaks, the peaks of those bars. If we mark the centers of the peaks and dot them, maybe make marks on the centers, then and we now use the straight lines to join all the marks, we will eventually come back to what we have here that is called frequency polygon. So it's just a conversion of these blocks that we have in histogram into line graph. Then the next is we can talk of charts. Like what we have is a pie chart. And pie chart is no other thing than segmenting a data set according to different categories. Just like we talked about, for instance, maybe the undergraduate nursing students. And we have noted that they belong to 4 different groups, 4 different years of study. Second year, third year, fourth year, and fifth year. Is it not so? Therefore, we can put them, the number. Somebody can build a pie chart of the what? The distribution of these students according to what? According to their year of study. And that can be put in a pie chart like this. Each segment, the size of each segment corresponds with what? The size of the group that has that particular segment. And another way similar to the pie chart is the bar chart. This is a bar chart. And we understand that bar chart is not the same as a histogram. This difference between a bar chart and the histogram is that in every bar chart there must be what? There must be spaces. Bar chart is a chart of freestanding bars. Each of the bar must be freestanding. And when we have it in that way, we have a bar chart. This is not the only type of bar chart. We have different types of bar charts. This is a simple bar chart. We equally have what we call a multiple bar chart, where we begin to have 2 compartments in each group. For instance, if somebody has looked at the same nursing students, second year, third year, fourth year, fifth year. In second year, there are males and females. In third year, there are males and females. In fourth year, males and females. In fifth year, males and females. So if one is going to put his chart it in such a way that the males and females are represented in each of the year of study, that becomes a multiple bar chart, where each bar will now have what? Two compartments, male, female. I hope it's clear. And in that same situation, we still have yet another type of bar chart that we call component bar chart that can be used instead of multiple bar chart. In such a situation, instead of putting each bar in compartments, we put it a single bar, but what? Segmented. In such a situation, we have it segmented. And the segmentation is going to be according to the size of each category of the data. I hope it's clear. So when we have all of them, that's what we know as a bar chart. So, with that, we have discussed all of them. The next thing that we want to look at is general steps in conducting tests of hypothesis. General steps that we have in conducting tests of hypothesis. We have discussed all the different tests of hypothesis that we can conduct, but we have general steps. All of them follow the same pattern. Whether you are doing F test, whether you are doing a T test, whether you are doing Z test, all of them follow the same sequence, step-by-step approach to conducting tests of hypothesis. Here, number one step is to state the null hypothesis. I can still change it, maybe permit me to say that it is to state the null and alternative hypothesis. That is number one step, to state the null and alternative hypothesis. Where the null hypothesis is usually stated to show non-significant results. Maybe you are testing that something is, the difference between two different groups is significant. If that is what you are interested in, the null hypothesis will be stated in such a way that there is what? Nullity. In other words, that there is no significant difference between them. That is the way the null hypothesis is always stated. I hope it's understood. You don't state null hypothesis to show a direction. It shows it is always made to be flat. That is usually stated to show non-significant results. Every null hypothesis everywhere shows non-significance. Also, the effort that is made in the entire test of hypothesis is to reject the null hypothesis. So, test of hypothesis is built in such a way that once a null hypothesis is stated, every effort is geared towards what? Rejecting it. That is what we do in test of hypothesis. We have stated the null hypothesis. It is possible that our interest in our research is on the alternative hypothesis. But we must first of all state a null hypothesis that will be negating that hypothesis which is our interest in our research. But in terms of hypothesis, our interest will be every single step is geared towards I want to reject the null hypothesis. The essence of doing that is if I reject it, I will now be able to know that this direction I am moving has been upheld by the data set that I have. I don't know if it's clear. So, in terms of hypothesis, we state the null and the alternative hypothesis. The null is always stated to show what? To show non-significance. While the alternative is stated to show what? Significance. Also, the effort is geared towards rejecting the null hypothesis. I don't want to say this here because it is just for us to report our research where people say we accept the null hypothesis. Technically, even though it is not very correct, but even in statistics department, we use it. So if we can use it in statistics department, it means anybody can use it. But in the actual sense, it is not good to accept a null hypothesis. If you don't reject it, that you have not rejected it does not make it to be correct, according to the theory of test of hypothesis. If you cannot reject a null hypothesis, what it means is that there is no sufficient evidence to reject it. That there is no sufficient evidence to reject something doesn't mean that there won't be sufficient evidence to reject that thing. I hope it's clear. What it simply means, I have a data set. From data set that I have tried to reject this null hypothesis based on the information I have in my data. But the information has not been able to do what? To reject it. And you end at that point. What I'm trying to say is that accepting null hypothesis is technically wrong, but I have given a leeway that even in the Department of Statistics we say it, that we accept null hypothesis. So if we can say it, if we can make that mistake in Statistics Department, it means anybody is free to make the mistake. I hope it's understood. So the simple example is said in a research to determine the effect of blood group in the time of recovery from an infection. We are looking at, is it possible that somebody's blood group affects his time of recovery for specified a particular infection? We will state our null hypothesis. We denote null hypothesis with H, not the way I wrote it here. This one is H0, but it's not H0. It is H subscript O, small letter O. That is the null hypothesis. H subscript O. So we set it to mean that the time of recovery does not affect. That is what it should be. So we state it to be, there is no significant effect of time of recovery, or sorry, of blood group in the time of recovery from the disease X or from the infection X. Another way of putting it is that blood group does not affect the time of recovery. I hope it's clear. Any other thing that is negates this becomes what? An alternative hypothesis. An alternative hypothesis, it depends on what we are interested in our research. There are different alternatives to this. Number one is that, yes, that blood group affects the time of recovery. That is the alternative hypothesis that can be used for this. But there are so many other tests that one may be conducting. You begin to see different types of alternative hypothesis for the same null hypothesis. But, okay, thank God it does not apply to this. So we move on. Step 2. When I have stated the null and the alternative hypothesis, the next step is to determine the level of significance for the study. And that means that every study has a level of significance. What do we mean by level of significance? Level of significance, by definition, is the maximum probability of committing type 1 error, by definition. Maximum probability of committing type 1 error. In terms of hypothesis, I was talking yesterday and I began to tell us that in statistics, that there is no result that is 100% correct in statistics. No result. That is the only thing that differentiates statistics from mathematics. Mathematical result is different from statistical result. The reason is because the statistical result has what? A margin of error. It has an allowable margin of error that is associated with any result that we are getting. But a mathematical result is deterministic. So it is always error-free. But in real life, we don't have issues that where there is error-free. Okay? Because of that, statistics builds in the error margin. So that if I'm trying to maybe make this conclusion, when I finish all the tests I'm going to conduct, and I'm reporting my results, and I'm making this conclusion based on my research, that's a conclusion I'm going to make has what? An error margin. And it is that error margin that you call what? Level of significance. The maximum probability of committing type 1 error. And what is type 1 error? Type 1 error is the error of rejecting a null hypothesis when it is not supposed to be rejected. That is type 1 error. There are two errors that are committed when we are testing hypothesis. Number 1 is type 1 error. Number 2 is type 2 error. Type 1 error is error of rejecting a hypothesis, which is a null hypothesis, which is not supposed to be rejected. Null hypothesis is not supposed to be rejected, and you go ahead to reject it. It is what? It's an error, and it's error of type 1. The next error is error of type 2, and that error is when you are supposed not to, how do I put it? When you are supposed to reject a null hypothesis, but you go ahead not to reject it, okay, to accept it. When you do that, you have committed an error. It's an error. Why? Because you have accepted something that is wrong. So type 2 error is the error of accepting a wrong null hypothesis, while type 1 error is the error of rejecting a true null hypothesis. What we usually build in the test of hypothesis is the error of type 1. And that's what we have called the margin of error. The error of rejecting a null hypothesis when it is not supposed to be rejected is always built in our test of hypothesis. And that is called level of significance. In a classroom work, we usually use a generic type 1 generic level of significance, which we always call 5%. 5% level of significance. And 5% is something as 0.05. Is it not so? But when we are conducting research, we must not always conduct our research at 5% level. The level of significance that we are going to give to our research should be matched with the sensitivity of the research. I hope it's clear. If it is a high sensitive research and you are putting maybe 5% error margin, you are giving up to 5% to be of error. You can imagine if it's something that requires maybe human life and you are making a conclusion with a up to 5% margin of error. What it simply means is that if there are up to 100 persons, that your conclusion is allowing that 5 will do what? 5 will go in because of that. Do you understand? So if it is highly sensitive research, we make the level of significance to be as small as possible. So the smaller the level of significance, the tighter the test is going to be and the result we are going to get. I hope it's understood. Like I have said in generic, these terms will always say 5% level of significance, but level of significance can be 1%, it can be 0.5%, and so on and so forth, depending on the extent to which we want the sensitivity of our research to be. Yes.
What you said in the previous slide for this, that are not hypothesis, that we aim at rejecting are not hypothesis. Then when you now talk about error, when you now know that there could be error, what if our data actually suggests that in reality that the null hypothesis should be rejected? Why at the issue our whole effort is to reject null hypothesis? Doesn't it lead us to like 2 errors?
Okay, no. The point I was making there is that the way test of hypothesis is built by the people that developed test of hypothesis. In the theory of test of hypothesis, the effort is to reject it. Okay? But even though the effort is to reject it, it doesn't require any special effort that you should add to reject it. Just to follow the procedure. But in the theory of test of hypothesis, that procedure you are following is trying to do what? Reject it. So that is the procedure you are following. The effort of that procedure is to reject that null hypothesis. But it's not for you maybe to help that procedure to reject it. Just to follow the procedure. At the end of the day, if the procedure succeeds in rejecting it, that is good. That is what you report. If you fail to reject it, you accept the alternative hypothesis. But whichever one that you are doing, there is an error that is attached to it. The error of rejecting it when you are not supposed to, even though the target is to reject it, but it is possible that it is rejected when it is actually not supposed to be rejected. And that is an error that is called error of type 1, which measures the level of significance that is given to a test of hypothesis. I don't know if I have answered your question. Yes.
Like now, at the end of your research, you now find out that instead of rejecting it, that your work kind of inclined towards accepting it. Can you still now go back and reject it under that error?
No. No. You have finished and your result shows that you should not reject it. You should accept. Is it not? So it is the output, the result of the hypothesis, test of hypothesis you have done. That is what you will report. So you will not go back. That which you have obtained as the output of the test of hypothesis, that is what you will report.
That thing you are reporting now is type 1 error.
How is it type 1 error?
You see, if you're supposed to reject and you will not reject, then you will not accept. And you have been following it duly. And at last, you will not accept.
If I understood what you have just brought in, the issue of the error is not for you to even know where it is coming from. it is inherent, it is inside that procedure that whatever thing you are going to achieve at the end has that margin of error attached to it. So it is not, you have no hands. You have no hands at all in it. The only thing is that as you are following that until whatever conclusion you arrive at, you report that conclusion. But in your mind, know that this conclusion that you have reported has some margin of error attached to it. Is it understood now? Now, yes.
How do we add it?
How do you add the level of significance? Do I have answer to that? But okay, well, maybe we will get to that. We are not trying to solve one particular test of hypothesis here, but we will get to that. You know, when you are testing hypothesis, they will ask you to choose your level of significance. And you maybe say, let me test at 5% level of significance. You have, it means that you have margin of error of 5%, which is 0.05. And that is now going to inform some values that you are going to use to arrive at the result that your test of hypothesis is arriving at. But we will come to that to see how that will come in. I think I have passed this. Yes. So number 3 is conduct the test using a given test statistic to obtain the p-value. I want to pattern this to one method. There are 2 different methods. Either we use p-value method or we use what we call the calculated value method. But I want to use, most softwares have as default the p-value method. Because of that, I will only discuss p-value method. That's what is called p-value. And what is p-value? P-value is the probability value by definition, probability value. What does it measure? It is the actual probability of rejecting the null hypothesis. The actual probability that is obtained from your sample. If you like, you call it the observed probability of committing the error of type 1. Okay? And how it is measured, softwares will always give the measure of the p-value. But I have told us what it is. The actual or the observed probability of committing the error of type 1 is p-value. So, we obtain the p-value using the data set that we have. When we have obtained the p-value, now the question will now come as we move to step 4. We compare the p-value with the what? The level of significance. This is where someone asks, how do we give the level of significance? And this is where it comes in. Is that person listening to me? This is where it comes in. I want to carry out this study at 5% level of significance. What it means is that I will be comparing my p-value. You know, as a probability value, every probability value ranges from where? From 0 to where? To 1. Is it not so? What makes a value a probability value is that it is between 0 and 1. So, because it is a p-value, the highest p-value will be 1. And the smallest p-value is 0. So we will be comparing with the, again, the probability of committing the error of type 1, which is level of significance, is equally what? Is equal to a probability value, which is between 0 and 1. But you cannot be carrying out a test of hypothesis, and you decide to give your level of significance, which is the allowable error of committing the error of type 1 to be very high. Do you understand? The higher the level of significance, the lower the what? The accuracy of whatever thing that you are reporting. Do you understand? Because of that, we always make level of significance to be as small as possible. But of course, it can be equal to 0. Because when it is equal to 0, it means that you want to report 100% accuracy, which is not possible. I hope it's clear. So we make it as small as possible. Assuming it is 0.05. That is where, assuming our level of significance is 0.05, which means we are testing at 5% level of significance. Is that clear? We will compare that level of significance with our p-value. P-value is another probability value. It is possible that our p-value is 0.23. We will be comparing 0.23 with what? 0.05. And then we will take a decision based on that. And that is that decision that we see in step 5. Decide whether or not to reject the null hypothesis based on the p-value and the level of significance you have chosen. And we said, note that if p-value is less than level of significance, if p-value is less than the level of significance, what do? We reject the null hypothesis. But if it is not so, we don't reject the null hypothesis. In other words, we accept the null hypothesis. So, if for instance we have obtained our p-value to be 0.04, okay? When we did the computation, we got our p-value for a particular test to be what? 0.04. Are you there? If we are to test at 5% level of significance, which is 0.05, what does it mean? We will reject the null hypothesis. Okay? Because we have tested at what? 5%. Do you understand? But if it is not so, if we are testing at 2%, we will see a different thing altogether. Is it not so? We'll have a different conclusion altogether. That is where the level of significance comes in. It decides, we use it to decide whether to reject or accept the null hypothesis.
And the p-value is exactly the same.
We say if it is less than. If it is exactly the same, you accept. Number 6 is make conclusion about the test based on the decision made in step 5. Note that there is no general conclusion about the null hypothesis. It's very important we note it. There is no general conclusion about the null hypothesis. You don't say, because I did this, I therefore reject the null hypothesis and conclude that like the issue that she presented, and conclude that the usage of library by these students depend on the year of study. If you stop at that point, you have not completed that. One, we need to know the margin of error at which you are making your conclusion. Therefore, we will say, for instance, since p-value is less than the level of significance, H0 is rejected, and conclusion is made that there is a significant effect of blood group in the time of recovery of X at level of significance of 0.05. It is that last clause that is important. It should always accompany our conclusion, so that somebody will know the level of significance at which you are making your conclusion. Do you understand? So there is no general conclusion. Every conclusion is dependent on the level of significance that you are testing. I hope it's clear. So when you are concluding, attach that level of significance so that your reader will know that you have made this conclusion based on this level of significance. Okay, if we are through with that, then we are done with those steps, general steps in test of hypothesis. We will go to the next, which we call measures of association. Measures of association. In statistics, there are two aspects of measures of association. There are two aspects. Number 1 is the regression, and number 2 is correlation. So when we talk of measures of association, we are invariably talking about one of two things. And those two things are what? Regression and correlation. Because by that we are looking at how associated the variables are. Whether it is regression, we are talking of how associated the variables are. Whether it is correlation, we are talking of association between what? Variables. So, we will start with the first one, which is the regression analysis. We do statistical study that where we are told that we are going to use regression analysis. Okay? So, what is regression analysis? In the first place, regression determines the nature of relationship between variables. The nature of relationship between variables. When we are talking of this nature of relationship, one of them could be inverse relationship. Is it true? Meaning that assuming we are looking at two variables, our interest is on two variables, and we are looking at the nature of relationship between these two variables. We are talking of what? Inverse. If there is inverse relationship, it means that as one is increasing, the other one is what? Decreasing. So we have noted that that is the nature of relationship existing between these two variables. There is possibility of a direct relationship or positive relationship, which means as one is increasing, the other one is also increasing. As one is decreasing, the other one is what? Decreasing. So that is what? A positive or direct relationship. That's the nature of relationship. There is equally a situation whereby there is no relationship. Maybe as one is increasing, the other one remains constant. I hope it's clear. So if whether one is increasing to Z or increasing to anywhere, the other one is not affected, it remains constant. That means there is what? No relationship between them. I hope it's clear. That is also a nature of what? Relationship. So when we are talking of nature of relationship, we use regression analysis to determine nature of relationship that exists amongst variables. The variables are usually in regression analysis. We usually have two types of variables in regression analysis. One we call the dependent variable. Another word for dependent variable is what? The response variable. Yet, another name for the response variable is what? The explained variable. And yet, another name for the explained variable is what? The regressand. So you can take any of these names. When we talk of response variable, we mean the dependent variable. The variable that depends on the other. Then the other type of variable is what we call the what? The independent variable, or the predictor variable, or the explanatory variable, or the regressor. It is that one that is called the independent variable. And what we do in regression analysis is to determine if the dependent variable actually depends on the independent variable, or to check the nature of relationship that exists between the dependent variable and the independent variable. That's what we do in regression analysis. In every regression analysis, there is always what? Only one dependent variable. In every regression analysis, there is always one dependent variable. But for the independent variable, there could be many independent variables. I'm sure it is clear. Is it understood?
No.
Hi. I wanted you to say yes, and you are saying no. Huh? So what is not understood there? You know, I'm asking you because your voice was the loudest.
Yeah, the independence from the doctor.
Mm-hmm. What is the problem with that?
So you were saying that the variables are usually one dependent.
Yes.
Or response.
Yes.
Mm-hmm.
Mm-hmm.
And I did not get the explanation you made about the depth of the dependence of the.
Okay. I says, and I repeat, that there is always a regression analysis. We have first of all known that what we use regression analysis to do is to determine the nature of the relationship that exists between the dependent variable and the independent variable or variables. We have noted that. But we now went further to say that in every regression analysis, there is always only one dependent variable, which can as well be called response variable, which can as well be called the explained variable or the regressand. There is always one of it in that regression. Okay? But for the independent variable, there could be many of them. Many independent. The reason is because one particular thing, one may be interested in checking if one particular thing is dependent on so many variables. I hope it's clear. So, because of that, that is what I said. And these independent variables, you can as well call them the predictor variables, or the explanatory variables, or the regressors. Is it understood now? Okay. Now, we'll go again. This nature of relationship that exists between among these variables may be linear. It may equally be what? Non-linear. When is it linear? It is linear if there is a kind of a straight line relationship between the variables, between the dependent and the independent variable. Once there is like a straight line relationship between them, we say that there is what? A linear relationship between them. Is that clear? But if it is not such, then we say that they have what? A non-linear relationship. Non-linearity can be captured or pictured in different ways. One of them is, we know what is an exponential curve. Every exponential is like a curve. Whenever we have a relationship that can be presented in the form of a curve, we will say that we have what? A non-linear relationship. Because linear, another way of explaining linear is what? Straight line. So there could be a straight line relationship between the variables. There could be a non-straight line relationship between the variables. Is that clear? Whenever the relationship between them is a straight line, we call it a linear relationship. When it is not a straight line, we call it what? Non-linear relationship. A simple, now, yes. Okay. No. Dependent variable, yes, is a regressor. Is the regressor, yes. When we are building regression analysis, we are looking at how the dependent variable depends on the independent variable. So it is the independent variable that controls the behavior of the dependent variable, if it actually depends on the independent variable. So it is the independent variable that regresses the dependent variable. The dependent variable, whichever way it will move in the course of maybe whatever thing you are checking, is dependent on the what? On the independent variable. So it is that is the regressor. That is the one that controls it. Do you understand? So it is the regressand. It is just there, waiting for the what? For the regressor to control it. Is it understood now? I have talked of linearity and non-linearity. So there is what we call simple linear regression. or simple regression in general, whether it is linear or non-linear, we have what we call simple regression. And when do we say that a regression is simple? I have told us before now that there could be many independent variables in a regression analysis. Is it not so? That's what I told us. Good. But when there is only one independent variable, we will say that that regression analysis is what? Is a simple regression analysis. Reason? Because it has only what? One independent variable. When we have more than one independent variables, we say it is what? A multiple regression analysis. Is that understood? Okay. So I have presented an example of what I call a simple linear regression model. That is what I presented. I hope you can see that. It is a simple linear regression model. Number one is that regression is what? Linear. Number two, it is what? Simple. Why is it simple? Because it has only one independent variable. And this model, the first one, which is the subject of this equation, is the one that depends on the independent variable. So the subject of this equation is the what? Is the dependent variable. I hope it's understood. Is it understood?
No.
You know, you don't know what is subject of an equation. Subject of an equation is always presented on the left-hand side of the equation. Do you understand? When we say let us make x the subject of the formula, you remember that? Because all of us did mathematics. So when I say subject of an equation, I mean subject of the formula. So in this expression, what is the subject of that formula? Yi. So the variable y is the response variable or the dependent variable. And we are trying to check here the nature of the relationship it has with what? Xi. Xi is the what? The independent variable. Or rather, x is the independent variable. Yy is the dependent variable. There is a terms that are there. Don't mind those terms. They are Greek letters. We have beta, not, and the beta one. Is it not so? And then we have this one, which is what? If you like, you may call it E. Even though maybe in Greek it becomes an epsilon. But then, if you like, you can call it E. So beta naught, beta 1, and epsilon are what we call the parameters of this model. They are the things, the coefficients of this model. Okay? Let's start with the last one. The last one is the epsilon, which is the error. We call it the error term. I have told us before that statistical relationships accommodate what? Error. So this is the error term. The error that is associated with whatever relationship that y has with what? X. But we look at beta naught and beta 1. What is beta naught? Beta naught is what we call the intercept coefficient. What do we mean by intercept? As intercept coefficient. With some, in other terms, in other materials, it may be called a constant. What does it mean? It means an amount of the amount of yi that does not depend on the independent variable. I hope it's understood. So what do I mean? I'm trying to see if I can use an example to present it so it will be understood. If one is trying to check okay. That's an example I'm trying to bring in. One is trying to conduct a research, and in the research, he is trying to find out if a particular maybe treatment, or if I may put it, maybe in your field, let me say, how a particular drug affects rate of recovery of patients. Do you understand that? We are looking at the nature of relationship between a drug and the what? Rate of recovery. What we'll be measuring is all the people that are suffering from that disease, they have become our what? Our participants, okay? That has become our study population. We select sample from the study population, sample of patients suffering from that particular disease, and they have been given this particular drug, okay? We are now measuring their what? The length of time that they will stay before they do what? They recover. You will agree with me that all of them are not going to, maybe, even if all of them are administered that particular drug in the same day, they will all not recover the same day. There will be variations in their recovery. Is it not so? Good. While we are trying to do that, there is need to build in a kind of control in such an experiment. There will be some that will not be given that drug at all. Those people may still recover. Do you understand? Good. But if they are recovering, their recovery does not depend on that drug. Is it not so? And what it then means is that when someone is suffering from that disease, whether the person takes the drug or not, that person will still do what? Recover. The only thing the drug does is that it does what? It fastens the time of the recovery. I hope it's clear. So, that recovery that those patients would have recovered, that are not captured, that are not being influenced by the activity of that drug, that is what? That is a constant. Whether you take the drug or you don't take the drug, you still recover. So it's a constant. It is the amount of the influence, amount of the effect of YI that is not affected by what? By the independent variable. Do you understand that? It is what this YI would have become that is not being contributed by what? By the independent variable. And that is what? Is a constant. I don't know if it's clear. Is it understood? Beta naught is what we are calling the constant. The yi is the what? The dependent variable. While xi is the independent variable. So it is the value of the dependent variable yi that is not being caused by the what? By the independent variable xi. That is that constant beta naught. Is it better understood now? Okay, so we'll call it a constant. This particular constant does not, the relationship between x and y does not affect it. Okay? It is a constant that is there. Whether there is x or there is no x, that constant is there. I hope it's clear. So that is, we call it the y-intercept or the constant. While the beta 1 is what? Is a coefficient of the x, the independent variable. What does it measure? It is the extent of change in the dependent variable that is being contributed by the independent variable. That is what it measures. And how do we mean? It is that unit change in the dependent variable that is being caused. Sorry, but that change in the dependent variable that is being caused by a unit change in the independent variable. That is this beta 1. Okay? But it is the beta 1 that measures the what? The influence of the independent variable on the dependent variable. Is understood? Okay. So once we have this, we have what is called the regression model. Well, And this regression model, the moment we have it, we will now be saying there are different values. It is these values of beta 1 that determines what we are going to report. Okay? It is because it is beta 1 that measures the what? The relationship between the dependent variable and the independent variable. Whatever is the beta 1 determines that relationship. But what we have discussed there is as it concerns a population. But we know in real life, we don't have any population to study because we may not get to the population. Because of that, when we collect a sample to build the same regression model on a sample instead on a population, we will now begin to estimate those values we have in the model, which are beta naught and beta 1. We will estimate them using the sample that we have to estimate them. Now, for us to do that, we will be estimating, and the type of estimation that we use here is such that we will set the error term to be what? To be 0, because we want to minimize the error. So we will set the error term to 0. And once it becomes 0, we will now be finding the values of the beta naught and beta 1. And here we have it, what we call the regression equation. It is this regression equation that is, another way for it is estimated regression model. It is this regression equation that is estimating the regression equation that exists in the population. But like I said, we don't have a population in real life to study. So we always resort to what? Study of sample. And because of that, we estimate the parameters of that population, and we have estimated the beta naught to be A, and then beta 1 to be what? B. And that gives that model. Yi is equal to A plus Bxi. It is, we obtain the A and the B on the assumption that the error term is minimum. We minimize the error term. And the barest minimum of error term is when it is equal to what? 0. So we use it to estimate the value of A and B. So when we do it based on a sample, we will obtain that B is equal to what? This formula that we have here is the formula for the estimated coefficient of X. The formula that we have there. And then A is equal to, using this formula that we have here, we obtain the estimator of what? Of beta naught. We may not bother ourselves so much with that. Maybe it was a mistake I made by putting it. So I should delete it. Yes. Okay, it's not a mistake.
No, sir. I said I was going to ask you because in data analysis, in chapter 3, the data analysis that I wrote, so the advanced statistics lecturer told us to use SPSS to analyze the question, and I became stuck in that place.
Why?
I don't even understand the SPSS.
Okay, you just joined the class now. Okay, because I have talked something about that. I said that the best thing is for you to learn to use those packages, statistical software, to be able to do the analysis by yourself. But whereby you cannot learn them, especially in the immediate, and they have something to do, there are people you can pay, and then you give them your data, and they will run the analysis and give you the results. And I'm sure the person that said that you should use SPSS, if you had asked further, the person will be able to direct you to someone that he or she knows that can do it. I didn't get what you said. The location is not a problem you can know someone that does something even while you are here. You know someone that does something over there. There are, it's because of the nature of research that people do. I know some people that do this kind of research that they will need to analyze a sample. Okay? For us, like in Nsukka there, I know people in chemistry department. For you to graduate as even a master's or PhD, they will ask you to go and get a sample somewhere, and once you get it, it has to be analyzed. And unfortunately, there's no equipment for this kind of analysis here. You will send the data, send your sample to somewhere, maybe in Canada, maybe in US, maybe in anywhere part of the world. They will analyze for you and send you results. So that's just to say that location is not a problem. What is important is that you can always get someone that will help you to do the analysis. But if you know how to do it by yourself, the better for you. At least you can do your own and do other people's own. Huh? No, I will not teach you. He said? Yes. Mm-hmm. Do you want me to answer? Some people have answered for you, for me, but if you want me to answer, I will say this. Can we listen? There is nothing wrong in contracting your analysis, both in internal defense and in external defense. There's nothing wrong. I don't know, some people, let's reduce the discussions, please. I hope we are getting what I'm saying. But then, the only thing that is wrong is that you do not know what was analyzed for you. That is the only thing that is wrong, that somebody will frown at. So when you have contracted someone to do analysis for you, when the person finishes it, you should be able to understand what was done. Okay? And once you have the understanding of what was done, you will be able to explain that. And that is, of course, what you are reporting. Because the person that did analysis for you will not report your work for you. You will report. And for you to report, you should have an understanding of what was analyzed for you. So the only time that somebody will frown at you is when you will not be able to, you don't know what was analyzed for you and you cannot report it. I hope it's clear. So nobody will frown at you that you contracted your analysis elsewhere. In research, where nobody will expect you to do everything by yourself. You may even be engaged in this kind of survey that will involve maybe massive population. You can even contract people to go as enumerators for you, to go and get data for you. Nobody will frown at that. But what somebody will frown at it if you don't know what the person or what those people you contracted have gone to the field to do. In research, nobody will expect you to start and finish everything by yourself, but you should know every stage of it. Okay, sorry, I will delete all these ones. No, they are part of that program. Okay, I will leave it, but okay, it is just there. It's all right. So when we have finished, sorry, there is this example. I say, suppose we want to obtain a simple linear regression of level of inactivity of a parasite on the volume of white blood cell in the body with data from 5 individuals. Now we have our level of inactivity to be the dependent variable, because while the volume of white blood cell is the what? independent variable. Is it not so? What it means is that the volume of the white blood cell affects the what? The activity or inactivity. Is it not so? So it is the independent variable, while the level of inactivity of the parasite is what? Is the dependent variable. So when we have this, we collected a sample from 5 individuals, while depending on the measure of or unit of measurement, we have our response variable, which is the level of inactivity 13, 28, 13, 11, and 14. Don't ask me the unit of measurement. What's important is that we just demonstrate it. It's just for demo purpose. While the volume of white blood cell is 4.5 for the first individual, 3.2, 6.2, 7.8, and 4.2. Is that clear? So when we have this, we want to build a simple linear regression equation on how does the level of inactivity of a parasite depend on the volume of white blood cell in the body. So we present it, all the x's, we present them here, then we will sum all of them. Total of all these 5 x's, we got what? 25.9. We come to the y, which is the what? The level of inactivity. We have all of them 13 to what? 14. When we sum them, we get what? 79. Then we are going to be multiplying x and y. Here we multiply 5.5 multiplied by 13 gives us what? 58.5. And we continue until the last one, 4.2 multiplied by 14, we got what? 58.8. So we sum all of this. When we sum them, we get what? 373.3. Is that clear? We come again to xi squared. Xi squared is the level of inactivity, the volume of white blood cells squared. When we have it, we have 4.5 squared is 20.25, 3.2 squared is 10.24, until 4.2 squared is what? 17.64. When we sum them, we get what? 147.41. We do the same thing for yi and we get this. And when we sum them, we get what? 1439. So, when we have all of this, it means that all the terms that we have in that formula that we had given before, we have obtained them. Our n is what? The sample size. And in that we have what? 5 individuals, which means our sample size is what? 5. And then we have a sum of xi. That place where we have xi, what is the sum we get there is what we will put here. Sum of x is the sum of what? The sum of the measurements we got as what? The volume of white blood cell. Whatever is the sum we put here, whatever is the sum of the levels of inactivity will be here. So when we have all of this, if we go back to the other slide, we are going to see that those sums are what we have here. So it is these sums that we have here that we will put back in those equations, on those formula that we have above. So when we have done that and we evaluate, we get this result. So estimated regression equation is what? Yi is equal to, we have used the two formula that we have given for B and A to obtain A to be 29.845 and obtain our B to be what? Minus 2.711. Is that clear? And so when we have that, I hope there's no problem with that. It is just direct substitution. I was thinking that we will say that is understood. See the point I'm trying to make. I will use something to explain that. What we have here is the sum of xy. Is it not so? What is the value that will be there? Sum of xy. So this is 737.3. That is what we will put there. But before then, we have n here, which is what? 5. So we will say 5 multiplying 373.3. Is that clear? Whatever it is what we will have here. Is that clear? We have sum of x multiply sum of y. And what do we have there? Sum of x is what? 25.9 multiplied by sum of y, which is what? 79. Whatever it is we will have, we will now take the difference between the two. When we take that difference, we will get a value. We will now go to the denominator. Sorry, we go to the denominator. What do we have in the denominator? We have n, which is what? 5, multiplied by sum of x squared. What is sum of x squared? Sum of x squared is 147.41. So we are going to do 5 multiplying 147.41. Whatever it is, we will keep it. And then come back again and get sum of x all squared. What is sum of x? We got sum of x to be what? We got 25.9. Is it not so? He says sum of x all squared. So we get 25.9 all squared. So whatever it is, we will find the difference between the two. When we have it, we will have a difference above, a difference under. We will now do what? Evaluate it. And when we do that, see what we got. The moment we did that, we got this value, which is minus 2.711. Is that clear? Now for us to obtain this one, we use again this formula that we presented here. For A is equal to sum of y. What is sum of y? We got it to be 79. Is it not so? 79 divided by 5 is the value that we have. Then minus that b, we have obtained the b before to be what? Minus 2.11. Is it not so? So we do sum of x multiplied by n. Sum of x is 25.9 divided by 5. Whatever it is, multiplied by what? Minus 2.11. Is that clear? Whatever it gives us, we will take this 79 divided by 5 minus whatever that gives us. And when we did that, we got this value, which is here, 29.845. So all that we now need to do is to carry the values we obtained for two of them and come to this regression equation that is here. This is the regression equation. So we come to this regression equation, yi equal to a plus bxi. So we look for that value that we obtained for a, put it here. Value that we obtained for b, put it there. And when we did that, we arrived at this equation, which means that yi is equal to 29.845 minus 2.711 xi. So this is the regression equation between these two variables, and those variables are the level of inactivity of a parasite and the volume of white blood cell. And when we look at it, we are going to see that first of all, the relationship between two of them is what? Is negative, is inverse, which means as the volume of white blood cell is increasing, then the level of inactivity of, or rather it should be level of activity of that white blood cell will be what? Will be decreasing, because there is what? Inverse relationship between them. I hope it's clear. So by having minus 2.711 shows this negative value shows that there is an inverse relationship. As one is increasing, the other one is what? Decreasing. That is what it has shown to us. Now, what does the 2.711 measure properly? What it measures is the extent for every unit, for every 1 unit change in the volume of white blood cell. There is what? There is 2.711 change in the level of inactivity. Do you understand? So this measures that extent of the what? Extent of change. It is this one that determines the change in the yi, in the dependent variable. The negative has shown us that there is an inverse relationship and it ends at that point. But even though this is negative, it could have been minus 0.0012. Is it not so? It could have still been minus 34.32. Is it not so? So there should be different values here. And what these values measure is the extent of change in this dependent variable y that is what? That is being affected by the independent variable xi. So for every just 1 unit of change in this independent variable, there is 2.711 change in the what? In the dependent variable. That is what it measures. So that is about us. Yes.
Because of that negative, because of that 2.7 that make it inverse.
Yes.
So if it is positive that is there.
It means there is a positive relationship between them. Meaning as one is increasing, the other one is increasing. Or as one is decreasing, the other one is decreasing.
So, do we take that xi as constant?
No.
What does it stand for?
It's the independent variable. We have looked at it. In this example, we use the two variables. One is volume of white blood cell. The other one is level of inactivity. What it means is that there is inverse relationship between what? Volume of white blood cell and level of inactivity. Is that clear? There's an inverse relationship between them. And it goes further to say that for every 1 unit change in the volume of white blood cell, there is what? There is 2.711 change in the volume of level of inactivity. Is that clear? That is what it measures. So, but we have just seen it on the surface. So we can now report this. Assuming we are doing regression analysis, we can report that there is what? There is a relationship that exists between y, the dependent variable, and x, the independent variable. Is that understood? You find out that this thing, if one wants to maybe have a set of data, one can fit this particular equation on a straight line. This equation that is here is a straight line equation. In other words, if I have different, one can as well, the essence of doing this is that it can be used for prediction. The essence of this regression analysis, building this model, is for the purpose of prediction. Okay? For instance, I see someone who has a certain volume of white blood cell. I will be asking, if the person has this parasite, what is the level of inactivity of that parasite? But first of all, you understand that we didn't use that particular person to build this equation. Do you understand? But having built this equation, we can now apply this equation to any other person in that study population. I hope it's clear. So that is why I said it is for the purpose of prediction. You are now predicting. Somebody will say, suppose someone has this volume of white blood cell. What will be the level of what? Inactivity. Do you understand? And you will put it. And that will be assumed to be what? To be correct. You can report it because it is correct. I hope it's clear. Yes?
There is no relationship. How will that be?
If there's no relationship. If there's no relationship between two of them, this 2.711 will be very close to 0, if not 0. Okay? Showing that there's no relationship between them. Like I have said, that what measures the relationship is this beta 1, which we have seen here to be 2.711. That measures the relationship. Yes?
There is an inverse relationship between y and x.
Mm-hmm.
So my question is not inverse linear. And 2x not.
No. Linearity is a different thing to inverse. Inverse is showing that as one is going up, the other is coming down. But then the relationship is a straight line. If one is to draw a straight line inverse relationship, it will take this form. This is a straight line inverse relationship. But if it is a straight line positive relationship, it will take this form. As this one is increasing, it's moving this way. Is that clear? But if it's inverse relationship, as this one is increasing, this one will be what? Decreasing. So the graph will be like this. There's no other question, right? Okay. Excuse me. I want to say again, it's not captured in the slides I have, but I want to say again that the type of regression analysis we have considered here is a regression analysis where this response variable is a continuous data set. Where this response variable, y, which is the dependent variable, is a continuous data set. Do you understand? You don't understand. I have told us before now that we have maybe different types of data. I started by saying that we have maybe even in the measured data that we have what we call the discrete data and the continuous data. I said that discrete data is when we have counting data. Like I used an example, number of something can never be what? Continuous. While we have another type of data where we have continuous data. I use an example like age. Age is a continuous data. There are so many, like maybe volume of anything is a continuous data, height is a continuous data, and so on. All these ones are continuous. But when we are talking of number of something, number of patients, it is what? Discrete. And because of that, I have now said that the type of regression, the regression that is done depends on the type of the data. Is that clear? This regression analysis that we just discussed is only when we have a continuous response variable. Is that understood? Like this here, I called it level of what? Inactivity. It should be continuous for this type of regression to be able to be carried out. Is that understood? Because there are basically three different assumptions in the regression analysis. We are not discussing the regression analysis in details, but if we are to do that, there are three basic assumptions of regression analysis. Number one is what we call normality assumption. The response variable is supposed to be normally distributed. It is supposed to follow a normal distribution. And the error term should equally follow a normal distribution. Number two assumption is what we call constant variance assumption. What do we mean by constant variance assumption? We mean that the variance of each of these observations is what? Is a constant. And the third assumption is independence assumption. And by that we mean that each of these observations, like we have used in this example that we solved, we use 5 different what? Human beings. So we assume that they are what? They are independent human beings. It is only when these three assumptions are satisfied that this type of regression becomes what? A perfect tool for analysis. But every other ones, it's important that I have said this. I have given these three assumptions. But most of the times, we may not bother ourselves as to whether these assumptions are satisfied or not, provided that we have this response variable to be what? A continuous data set. We have a reason for that in statistics. The reason is because every data, especially every continuous data in statistics, as it becomes large, it approximates to what? Normal distribution. So because of that, which we call the large sample theory, So because of that, once we have it to be the response variable to be a continuous variable, we can go ahead and use this regression analysis that we have done. Is that clear? Now, the reason that I have to say this is because there are other types of regression analysis. Very important. When we have a set of data where the response variable is not continuous, where it is discrete, there are regression analyses that have been developed in the literature for handling that type of situation when we have non-continuous response variable. And I will mention two of them that I know may be used in your fields of study. One is what we call the Poisson regression. Poisson is somebody's name. P-O-S-I-S-S-O-N. It's not poison. Poisson. Poisson regression analysis is an analysis that is devoted to handling discrete response variables. Another type of regression analysis that is devoted to that type of data is what we call what is the name again? Logistic regression. Logistic regression analysis. These two types of regression are used to handle discrete data. Particularly, logistic regression is actually used to handle nominal data. When we have nominal response variable, we can subject it to regression analysis using logistic regression analysis. But if we just have discrete response variable, then it can be subjected to Poisson regression analysis. I'm sure it's understood. The details of them we will not be able to discuss in here because they are not the conventional regression analysis that we know. But it's important that we understand them. And I'm sure that if you ask statistical softwares to handle, to conduct, or to carry out logistic regression analysis for you, it will be able to do that. If you ask the same software to handle Poisson regression analysis for you, it will be able to do that. But what is important is for us to know the type of regression analysis that we can use depending on the type of data that we have. Is that clear? Is it understood? Or this one is a classical regression analysis. If we want to give it a name, it's classical. It's not only that is called a classical. In statistics, any statistical technique that is based on normality is usually regarded as a classical statistics. Okay? And we have said that it is based on normality, so it is a classical classical regression analysis. The next part is correlation. The next part of that big study that we have started, which we call measures of association, we have dispensed with regression analysis, so we are going to do justice to correlation analysis. So we have discussed before now that regression analysis does something, and what does it do? It determines what? The nature of relationship that exists between or among variables. That's what regression analysis does. But then correlation, what does it do? Correlation on itself looks at the extent of the relationship, the degree of the relationship. Is that clear? In other words, one can do regression analysis and correlation analysis together. Regression analysis shows that there is what? The nature, a pattern of relationship that exists. But in that pattern, it will not tell us the extent or the degree of that relationship in that pattern. It will only tell us that there is what? Inverse relationship, for instance, between two variables. But the extent of the inverse, it may not show us. But when we go into now looking at the degree, the extent of that relationship, we can do what? Correlation analysis. So correlation analysis looks at what? The degree of the relationship that exists between variables. There are different types of correlation analysis. Number one is bivariate correlation. Number two is partial correlation. We have what we call multiple correlation, and we have what we call canonical correlation. All of them is just for completeness. We will discuss only one, the one that you know, the one that majority of you have heard of. That is the one that we are going to be interested in. So those other ones that we are mentioning is just for completeness. So what is bivariate correlation? Bivariate correlation analysis is simply a correlation analysis between only what? Two variables. I have said again that bivariate, by from the name bi means what? Two. So bivariate correlation analysis is correlation analysis between two variables. So when we are interested in building a correlation analysis between two variables, we call it a bivariate correlation. And that, I'm sure for some of you that have known correlation coefficient before now, it is that type of correlation coefficient that you know, bivariate correlation. Okay? But apart from that, there are other correlation coefficients that exist in practice. Number one of them is partial correlation. What is partial correlation? It is possible that you are trying to build correlation between two variables, but you want to build the correlation between two variables in the presence of another variable, where another variable is held constant. When we are doing that, we will call it partial correlation coefficient. It is a partial correlation is a correlation between what? A bivariate correlation between two variables in the presence of another variable, when that another variable is held constant. It will not give the same result with the bivariate correlation. Do you understand? Assuming I have a set of data for x1 as the first variable, x2 as the second variable, and x3 as the third variable, and I decide to do bivariate correlation between x1 and x2, I will get a result. But if I now decide to do partial correlation between x1 and x2 in the presence And what is Rx bar? What is Ry bar? They are very simple. We call this Spearman's rank correlation coefficient. What it does is that it ranks numbers. It doesn't compute the correlation coefficient from the actual values. Instead of computing, it resorts to, that's why it is called a non-parametric statistics. It does what? It will come and rank the observations. When it has finished ranking the observations, it will throw away those observations and use the ranks to do the computation. Do you understand? Let's maybe try to get it. Remove this one. For instance, in these x values, can we see that? Can we see the x values? Yes. 4.5, 3.2, 6.2, 7.8, 4.2. If we are using Spearman's rank correlation coefficient, we are not interested, Spearman is not interested in these values. It is only interested in their ranks. So what we will do is to begin to rank them in an ascending order of magnitude. Is that clear? Which means 3.2 will be ranked 1. Is it not so? Yes. 4.2 will be ranked 2. 4.5 will be ranked 3. 6.2 will be ranked 4. And 7.8 will be ranked 5. So Spearman's rank correlation coefficient has nothing to do with these values. It will now resort to the use of their ranks instead of the actual values. Is that clear? So when we see R subscript X, it means what? The ranks of X. Is that clear? The same thing, it will rank Y. When we see R subscript Y, it means what? Ranks of Y. Then when we see Rx bar, what does it mean? Anytime we see bar in statistics, it suggests an average. Anything bar suggests an average of all the values. So bar means what? When we take the what? The mean of those ranks. Rx bar means the mean of the ranks of X. Ry bar means the mean of the ranks of what? Y. So when we have all of them, we will use them to obtain, we will substitute them in this formula that we have here. It will give us a result, and that result is the Spearman's rank correlation coefficient. I'm sure it is understood. I will not want to explain this last one because we don't have the information in any of the slides for me to be able to explain that. Like we talk of DI squared. There's no place. DI simply means the deviations. Okay, I think we can explain that. DI means deviations. Like here, if I have ranked X, to be X will now be what? This will be 3, 2, I will have what? This is 3, 1, 4, 5, 2. That is what it is, you know. 4.5 is ranked 3. 3.2 is ranked 1. 6.2 is ranked 4. 7.5 is ranked 5. 4.2 is ranked what? 2. So when we have those ranks, we come to Y. 13 is ranked 1. 11 is ranked 1. 13 is ranked 2. There's another 13 that is ranked 2. Okay? Whenever we come in contact with this, there's a way to do it. Because 2 of them will now take the 2 consecutive positions. And because they are taking the 2 consecutive positions, we will give each of them average of those 2 consecutive positions. What am I saying? Like this first 13 is supposed to be the second, number 2, and the second 13 will be number 3. Is it not so? So 3 and the 2, we take average of 3 and the 2. That will be 2.5, 2.5. So we share 2.5 to 13 and 2.5 to the other 13. Is that clear? When we have done that, it means we have taken the third position. We are now coming to the fourth. 14 will be the fourth, and the 28 will be the fifth. Is it not so? So when we have it in that way, we now begin to, the deviations di will be d1, which is the first deviation, will be position of 4.5, which is what? 3, minus position of 13, which is what? 2.5. Do we understand that? So the d1 is what? 0.5, because it's 3 minus 2.5. Is it not so? We'll come to the second one. 3.2 is number 1 in the ranks of x, while 28 is number what? 5 in the second, in the ranks of y. So we will take what? 1 minus 5, and that will be equal to what? Minus 4. 1 minus 5 is minus 4. That will be d2, the second deviation. We will do the same until we get to the last one. Is understood? So when we have obtained these deviations, we begin to square them. We'll find out that the first one, which is 0.5, d1 squared will now be what? Square root of, square of 0.5 is what? 0.25. So the first one will be d1 squared is 0.25. The second one, which is d2 squared, will now be what? Minus 4 squared, which is what? 16. I hope it's clear until we get to the end. When we get to the end, the sum of all the di squares is the sum of all of them. And when we have that, that is what we are going to substitute here as sum of di squared, which we are going to multiply by what? 6. 6 multiplied the sum of di squares is the numerator we have here. When we check that data set, our n is equal to what? 5. Is it not so? Our n is sample size, which is 5. So here is 5 squared is what? 25. So we'll be discussing 25 minus 1 is what? 24 multiplied by this first 5, which is what? Whatever thing it is, 5 multiplied by 24. Whatever thing we have, we are now going to do what? Evaluate it. When we have evaluated it, we will take 1 minus whatever thing that ratio is. Is that clear? Whatever thing it gives us becomes the what? The Spearman's rank correlation coefficient between the two random variables. Okay, you are reminding me that you are going to do meta-analysis. Okay. So what do you want me to say? I should say yes or no? I have not mentioned the meta-analysis today, except that you have started it. Maybe very soon we will come and you will tell us what is meta-analysis. Why wouldn't you know it? So let's discuss characteristics of bivariate correlation. Characteristics of bivariate correlation coefficients. We'll look at the characteristics of them. Number 1 is that every bivariate correlation coefficient is between -1 and 1. Did you hear what I said? If you are asked to find the correlation between two variables, the values you are going to obtain must be between -1 and 1. You cannot be doing correlation coefficient using any of these two methods that I have explained to us, either Pearson's product moment or Spearman's rank correlation. You cannot be doing correlation coefficient using any two of them, and you get a value like maybe 2 to be the answer. The correlation coefficient is not true. Whatever method you are using, the correlation coefficient must be between what? -1 and 1. That is the range of values of bivariate correlation coefficient. That's number 1. Number 2 characteristic is that when it takes the value 0, when the correlation coefficient takes the value 0, it means that there is no linear relationship between the two variables. It means that there is no relationship between them. Is that clear? That is the meaning of correlation coefficient of 0. They are not related. That is the meaning of that. Now, number 3, when it assumes the value of 1 plus 1, it means that there is what? A perfect positive relationship between the two variables. When it assumes the value plus 1, it means perfect positive relationship. And when it assumes the value minus 1, it means perfect inverse relationship. Is that clear? Again, when the correlation coefficient is greater than 0, it means that there is what? A positive relationship between them, which in other words simply means that the slope between the variables is positive, which means that as one is increasing, the other is also what? Increasing. And when it is negative, when it is less than 0, meaning it is becoming negative, it means that there is negative or inverse relationship, which means as one variable is increasing, the other one is what? Decreasing. And having stated this, it's equally important that we say values in between 1 and the minus 1 indicate how strong or how weak the relationships may be. The reason is because it must not be 1, it must not be minus 1, it must not be 0. It can be values in between minus 1 and 1. And that is why we talk about what? The degree or the strength of relationship. So they measure the strength of the relationship between them. In other words, when it is close to 0, it means that the relationship between them is weak. We have said that when it is 0, it means what? That there is no relationship. So when it is close to 0, whether it is positively close to 0 or negatively close to 0, what it means is that there is what? A weak relationship between them. Then when it is maybe close to 0.5, one may say that there is what? A strong relationship between them. Whether it is positive 0.5 or negative 0.5. I hope it's understood. So maybe if it is like when you have a correlation coefficient of like 0.7, one can say that there is what? There is a very strong positive correlation between the variables. Then when it is minus 0.7, one will say there is a very strong negative or inverse correlation or relationship between the variables. That is taken. The last thing that we will say there is that if x and y are independent, that's what we call independent variables. But if x and y are independent, it means that the variables are, that their correlation coefficient will be 0. But however, I said that when correlation coefficient is 0, it does not mean necessarily that they are what? Independent. So, in other words, 0 correlation means what? Sorry, independence means what? 0 correlation. But 0 correlation does not mean independence. So, we have taken that, and I don't know, the faculty rep is not here. I wanted to ask for something. Just give me 1 minute. Let me get her. I said 1. Oh. So, well done. Where is Dr. Zibo? So she's not within here. I wanted to rest.
Okay.
No. What I mean is that I can't be resting. The students